This is the Cornell Energy Recovery Linear Accelerator project. Cornell currently has a synchrotron on campus connected to the Wilson lab. And if you go there today, it's a very cramped, older facility. The science is new, but the facilities are definitely dated. This new facility is going to provide them a lot better program so they can carry out this science.
The ERL accelerator is actually a bigger machine than our current storage ring. In circular size, we're about 760 meters in diameter. The new one will loop quite a bit further out, a total path length of 2 kilometers. And need to, for the energy recovery LINAC machine, add these pink buildings that you see here and bore an additional tunnel out underneath the vet part of the campus.
ERL extension of the current facility would provide to X-ray science researchers a beam that is at least 100 times more brilliant than anything that's now available in this type of X-ray machine.
This project is a unique combination of a building and infrastructure tied together. The tunnel actually passes through the basement of the building. The building is actually set with 3 levels into the side of the hill. So it's not a building on top of it on land in a conventional way, it's set into the hill.
We use the building poetically almost to hold up the hill. So stepping the building against this hill really gave us a great opportunity to do a lot of different things. You wouldn't actually even see the building from many different aspects of Cornell University. You'd see over the building. So we kept a lot of green space. All the roofs would end up being green. Some of the roofs you could actually walk on. So the building very comfortably tucked into the landscape, but it certainly was a structural challenge to make it all work.
Well, the project itself will comprise a series of tunnels linking into the existing LINAC ring at Cornell and the construction of a new laboratory.
The beam that's already there is the beam that's going to be extended through this new building and through the tunnel. All has to be absolutely at the same level. So the location of this building is set by that physics already.
We've designed a stiff retaining system of interlocking secant piles, which will be installed into the ground to allow the ground to be cut away before any of the tunneling can take place.
The tunnel that we were tasked to design was not a particularly remarkable, it did not seem like a particularly remarkable tunnel at first. But the more we got involved in the project, we realized there were more unique considerations that we weren't so used to designing for.
It sort of goes back to some of the subway experience that we've done in terms of the fact you're digging a big tunnel underground and you're trying to ventilate it and trying to run services inside. I liken it to kind of like a submarine where you have a really tight constrained space and you're trying to run all this stuff in. And the more space you take up, the more money you spend. So there's a lot of pressure on you to be as economical as possible when you do these type of designs.
When we asked Maury and his team what sort of settlement tolerances they're willing to live with, he said, well, I don't know, about, can you keep it less than 50 microns? Which is something which, you know, as a civil engineer, you just don't have to deal with those sorts of scales.
When you have the client who wants something, when you have the site, when you have the whole college and the whole master plan working all in concert, all of that together starts giving you the opportunities to really have a great building.
Oh, I think we've hit it just very nicely. The Arup team has done a very nice job of working with us to put together some structures that scientifically make a lot of sense and visually are exciting.
It would be an enormous plus for Cornell, not only because it would support unique frontier research by Cornell students, staff, and faculty members, but it would also bring people from all over the world.
It means we'll be ahead of the curve by very large, substantial factors, and if we prove the technology to work as well as it looks like it could do on paper, then other people will want to copy this technology and upgrade their circular accelerators into an energy recovery LINAC.